Welcome back. We had a nice break. So today we're going to talk about pairs data, matched pairs data. But there's a question about the schedule a little bit, so might as well talk about that just a bit. Homework is due not on Wednesday as originally planned, but actually here on Friday. That's been announced, that's posted, so it's due on Friday. The second exam is in class next Wednesday, right? So that's a week from Wednesday. So you turn in that homework, it'll cover mostly the material from homeworks 5, 6, 7, 8, the 4 that we've had since the last exam. We'll have a review day on Monday and then the exam on Wednesday. And then sometime this week I'll post review problems and things like that to go over. I'll try to have the homework solutions posted kind of on the weekend or at least early Monday morning, so that you can look at those as well. Right? It's a little bit off from what's exactly listed day by day there, but we're covering the material, and today we're going to talk about matched pairs data, where the data are quantitative, but we have two measurements on the same unit, or the subjects themselves are paired together, and there's one measurement on each one, and somehow it's linked together. So, but any questions about it? So in matched pairs data, we have quantitative measurements. X and Y. And we have in subjects in all, and each variable is measured on each subject, or each pair, right? Subjects, pairs, like that. So the data structure can look like this, where we have X and Y measured, right? And then on the first unit we have X1, Y1. On the second pair we have X2, Y2, etc. down to the last one, number n, X of n, Y sub n. Okay. And so we could summarize the X variables and the Y variables separately, but these are really associated with each other. Scenarios where we use this is kind of before, after, so maybe X is the initial measurement, maybe at baseline, and Y is the measurement at 3 years out. Or there's two measurements at the same time on an individual, so you take a test, there's a reading portion, a verbal, there's a math portion, so you'd have two correlated measurements, or maybe two different, within one math test you might have two different scales, one related to algebra, one related to geometry, and so there's two parts of it. In other cases, there are two individuals that are put together. It's called a case control study, where one person has the disease and one person does not, but you're measuring their comparison on some other thing, right? Some other value. There's some linkage that's made explicit there for a design purpose. And so instead of doing them just separately, we're going to take the differences. So say D is Y minus X. Sometimes you might take X minus Y, and whatever the context is, you have to think about what it means to take the difference. But so then in this D1 is going to be Y1 minus X1, and D2 is going to be Y2 minus X2, etc. And the last one is D sub n is Y sub n minus X sub n. Okay. And so we have n measurements of n differences. Okay. And so we're going to summarize that just like we would summarize one sample. We're going to do the average of those differences, we're going to do the standard deviation of those differences. And so in formulas, d bar, average d, is the sum 1 over n of the d1 plus d2 plus d sub n, or 1 over n using the summation notation, I going from 1 up to n of the d sub i's. Add up all the d's and divide by the number you have. And the standard deviation of the d's, which we'll primarily get from the computer, the S of d. How do we get a standard deviation? Well, we take a di minus its average squared. Take each of the differences minus the average difference, square it, add all those up across all I going from 1 to n cases, divide all that by n minus 1, take square root of the entire thing. So this is the standard deviation, sample average, sample standard deviation for the differences. Those are going to be our two basic summaries. Right? And so we're going to do what we're interested in. The parameter we're interested in is the average difference. Right? And so we're going to use the sample average, so these sample values. We're going to use those sample values to look at what we think the average difference is in the real population. So instead of having n observations, if we had the entire population, what would be the average of y versus x? So our parameter that we're going to be, as I said, interested in is the average difference. Average difference. It's equivalent to the average of the y's minus the average of the x. Depending on the context and what these variables mean, you might take the average the other way, the difference the other way, but we're going to take the y bar or the differences that way, so that's what we're interested in. So we can either do a confidence interval for this, our formula for our confidence intervals is going to be our d bar, that's our average in the sample, right? Plus or minus a t value. And how does our table? I use a t value from the normal table. So 95%, we're going to 0.975. We're going to use that, 0.975. With our degrees of freedom. Our degrees of freedom is the number of pairs minus 1. We have two in measurements, in on x and on y, but they're correlated and we're taking differences. And then the standard error is the standard deviation of the differences divided by the square root of it. So this whole thing here is the standard error. So this is actually a 95% confidence interval because I'm using the 0.975 there. So that's going to be 95% confidence interval for that average difference. To give you an idea of how big those differences are if you apply this to a population rather than just a sample in observations, right? Is the difference all positive? Is it all negative? Does it straddle 0? What are the ranges we could be interested in? Right? The other main way we're going to do is a hypothesis test. Right? So we're going to do a hypothesis test for this parameter. We're often interested in, is the difference 0 or not? Right? Is there a change, positive change? Is there a negative change? Is the average different? But we can be a little bit more general. Go to the next page. So we can do a hypothesis that the average difference is some delta. Delta is the hypothesized average difference. Versus, that it's not that. Often, that delta is just 0, right? No change. But it could be some other value. So that's a possibility there. So to do that, we're going to do a t-statistic. We're going to take our sample d bar minus that hypothesized value over the standard error. And that standard error is the same thing we used in our confidence interval, S of d over the square root of n. And we're going to compare that to a t-distribution. Right? And so if it's extreme, if it's a lot of standard deviations away from that delta, right, then delta doesn't seem too reasonable. But if it's not too many standard deviations, standard errors away, kind of relatively close to the standard error distance, then we're not going to be too surprised and we're not going to reject it. We compare this to a t-distribution within -1 degrees of freedom. And if it's very large, larger than, say, the 0.05 tail error, right, we're going to reject it. So our plan is to look at this in a few examples. Right? Do at least one of them by hand, look at how it gets done on R, and talk about a couple of interpretations. In a way, this is very similar to doing just a one-sample t-test, right, or a one-sample confidence interval for me. But instead of just having one set of measurements, we've taken the differences. But any questions? So let's look at actually the third example. These are problems from a different textbook. When I taught at George Washington University, was the book that we used. I like these examples because they kind of represent realistic data and actually show you the differences. So let's look at the one that's 9.47 for the traffic lights. Take a moment to read through what that one is about. Red light. Yes.
Yeah, okay, got it.
We have another one. What are you going to answer? Right, so there's a lot of description there, but the essence is they got some traffic lights. They had a number of accidents per year on average. Had a bunch of it at 13 intersections. They put in these red light cameras. You know what these red light cameras are? So they're cameras that are looking at your car, and if you go through the intersection sufficiently after it turns yellow and red, but then it flashes and takes a picture of your license plate in your car, and then they'll send you a ticket in the mail. Right? They're very popular around Washington, D.C. To try and slow people down. They have sometimes some of them are fixed point cameras around schools. If you're going more than 7 miles over the speed limit around the schools, right? They will take a picture of your license and send you that. There's ones that also you're stopping, right, that are particularly get a lot of people because, you know, say it's turning yellow and then it turns red and you stop but go a few inches over the line, like right at the crosswalk, and you know, then it will take a picture of your car and send you a thing that you've gone past it. But you know, it's a city, 4 or 5 million people. It slows down traffic. It creates some funny things like people driving exactly 6 miles over the speed limit because there's a little safety, a little buffer in there. But anyway, is it effective? Does it decrease accidents? Right? So this is called a before-after study because you have a bunch of places that are measured before and those same places are measured after. So the pairs are created because it's the same 13 intersections both times. Right? And so if you take after minus before and you get a negative value like negative 2.24 there, right? It's negative, that means before is larger, right? So there's fewer, you know, negative values when it's done this way is good, meaning that it's a decrease. Right. So a few summaries of this. We want to, we have the differences, the average difference. Well, there's 13 intersections used, right? The average decrease is 0.069. the standard deviation of those decreases of that difference column is 1.209. The standard error we're going to use in things, the standard deviation over the square root of n, 1.209 over the square root of 13. The standard error of 0.2354
Plus two.
We're going to be interested in, so you want to do 95% confidence interval. For the difference in average accidents. You'll go away a bit. And we're taking after minus before. Whenever you do these things, you just have to keep track of what a positive or negative means, right? In this case, a negative is going to mean that there's more before, and that means that's a good thing, so we want negative. So if we do a confidence interval, we need a t-value, right? We have degrees of freedom. What's the degrees of freedom? It's just 12. Right, what's our t-value that we need? T-table, 95%. We don't look at the 95 column, we look in this one. There's 95 leaves 5% on the side, so there's 95 in the middle, and that extra 2.5. Look at that one. And degrees of freedom 12. Right, so we're going to look across here and find this value. 2.179. That's a value from the t-distribution. That's the same in all problems where we have degrees of freedom 12. Right? So our t-value, the 0.975 with 12, is 2.179. So the confidence interval formula is the average plus or minus the t-value times the standard error. I'll write that on the next page. So d bar plus or minus our t-value times standard error. Plugging those things in negative 1.0069 plus or minus 2.179. And the standard error was 0.3354. Our interval, the lower part, is negative 1.74 up to negative 0.28. So accidents per year. So what do you think of these traffic lights? These red light cameras. At intersections of this sort, does it seem to make a difference? Yes.
Well, the numbers definitely decreased, so it's helping the crash.
Yeah. So these intersections, on average, when we do inference for the population of similar intersections, probably wouldn't want to take this to a rural intersection in Vermont and think about applying that there, but in the intersections that are similar in the Virginia, DC metro area, probably also similar in Boston or Chicago or LA or other cities of comparable size and complexity, right? It seems to decrease. Right? And that's good. Are we sure that the red lights caused this decrease? So this 95%, we can say definitely 95% confident that average change is in this interval. And the interval covers it actually, and it's negative, which means it decreased. So we're happy about that. Right? And then the further question becomes causation. Are we sure did the red lights cameras exactly. Are we sure that it was due to them? But anything else have done it? Yeah.
I think it could have been the presence of the cameras.
So, kind of the presence of the cameras or the fact that it gives tickets. So, I mean, they could have put just a sign that says cameras and put up something that wasn't doing anything. And people would think there's cameras there. So maybe it's not actually giving out tickets. It's putting up something that people think it's doing something, right? So there could be that psychological aspect. But that's kind of the same thing. But even if it was that, right? Well, what else was happening during that time, before and after? Right? Could there have been news coverage about this? Do people see construction alongside the road and say, oh, there's something going on, I better slow down? Is it really the red light cameras, or something like that? Maybe if it's summertime versus wintertime, maybe there's different traffic flows. Maybe other roads have expanded to compensate, and so traffic volume's down, right? So maybe there could be a number of things. So, but there could be confounding. So other factors that are in effect or change from before to after could have impacted the outcome. And so it's hard to conclude that it's just the traffic lights and the red camera lights. There could have been other things happening at the same time, and so there's a little bit of a question. Now, it's encouraging that it's decreased and it's significant in terms of that, but they might have wanted to do something else. But this is more of an observational study, right? You just have these 13, you observe what happens in them. What's one thing that's lacking in this type of study? Yeah.
Well, we don't have the other factors that could be impacting.
Yeah, you don't have those. You don't know that kind of macro trends or whatever is going on, right? But what else do we have typically in an experiment? Yeah.
A control.
We typically have a control group, right? So we don't have the lights where nothing is done. What if they are also decreasing about the same rate, right? Then we would see no real net benefit over just the rest, right? So an alternative type of study would be called a comparative before and after. So let's say you had 26 lights where you have concerns, and you flip a coin. Well, you measure them all before, right? And then you flip a coin, and then some of them, 13 of them, get the red light cameras. And 13 have no change. And then you measure after. So you can do before after in the treatment group, and you can do before after in the control group, right? And then if you see a bigger decrease here, well, if they have the same types of things going on, same population change, same news change, same news information going out there, etc. Right? If you still see a bigger gain here, in terms of improvement of the situation versus this one, over the course, same course of history, same course of time, then you're more convinced. Particularly if things got better here, but things got worse down here, right? It's a clearer message that there is a significant change. Once you get to 2 independent samples, this is really 2 sample methods. We'll do those on Wednesday. So instead of just having 1 sample, we have 2 independent samples, and we're comparing the average change in these 2 things. We'll do methods for that. would it be more convincing? There's another effect that goes on called regression to the mean. It affects the number of traffic accidents, it affects people's health, it affects scores on exams, it affects performance of sports players. But the individuals who are above the mean by a certain number of standard deviations, if there's a positive correlation over time, tend to be above the average again, but not nearly so far away. And the people that are below, right, a certain number of standard deviations, tend to still be below if there's a positive correlation, but not quite as far away, right? And this is an effect that Galton and others noticed throughout history, and there's mathematical reasons for it. But to state that so individuals who measure above or below the mean when there's a situation with positive correlation. Tend to measure again above or below consistent the mean at the new time period, but not as many standard deviations away. So that if you pick the 13 worst traffic intersections, they're still probably going to be pretty bad. But in comparison to the entire population the second time, they're going to be a little bit less. There's a little bit of reduction. So these cameras, these intersections had a benefit. Right? They had fewer accidents. It's statistically significant. But part of that is just this natural regression to the mean if they pick the worst ones. So in addition to confounding being there's just this slight reduction relationship, making it less. And a comparative study would show the natural regression to the mean of ones that aren't treated. So again, you kind of address this. Right? But we'll return to this when we do regression correlation after the regression. Forward, regression. We'll return to this when we do regression and correlation. We'll have a formula for it. Right? There's a way that would happen. But that also makes it hard to assign causation unless you actually have a control group. Right? So the benefit of a control group comes into play. But we can do a t-test, right? We can also do a test. We can do this hypothesis test. In this case, we're interested, is the difference 0? Right? No difference. Versus an alternative that is not 0. You might want to convince yourself that you can look just one direction. These new traffic lights create some distortions as well. People are, kind of watching them, or kind of gaming it a little bit and trying to go just over the speed limit. They're kind of watching their speed limit more than they're watching other cars. So it creates a kind of a different activity for your brain to do than simply drive. Right? But anyway, so if it's not equal, we calculate the t statistic. When it's 0, it's just d bar, and we're subtracting 0 technically, but it doesn't make any difference over the standard error. And that was d bar over s of d over the square root of n, all that denominator. That diagonal will be about 3, negative 3, so there's a negative decrease. We compare this to a t distribution with n minus 1 degrees of freedom. The 975 cutoff of that was our 2.179. Right? And so a picture of a t distribution. Here's 0. Right, here's 2.179. And here's negative 2.179. And And our value is out here. So it's unusual. It's far out in the tail. It's not something you would expect every day. Yes?
Could you just scroll up a little bit?
Yeah.
Thank you.
So our t-statistic is more extreme than the cutoff. So again, we reject 0. And the confidence interval didn't include 0. We reject 0 in a hypothesis. We're rejecting the hypothesis. It's not 0. In fact, we see that it's a decrease. So the red light cameras have fewer accidents. All right, let's look at another example. So 9.39 is on the handling of museum objects. This is rejected. So another example of this. 9. So how would you summarize what's going on in this study? What exactly have they done? Is it similar to the other one? This is another, before-after type of study. So there's patients. I don't know the context. Are these long-term patients? Are these elderly patients? Are they're obviously there long enough to be able to participate in something like this. And then there's some measurement of health status. It could be based on how they feel. It could be on a number of objective factors. In terms of respiratory and other things. So a complex measurement. And before and after. It doesn't say exactly what the time frame is, how far before and how far after. Exactly. But you kind of want to know. There's a journal article, so you could actually find it to learn more.
This is a real study.
Yeah.
That's so weird.
Yeah,
Who
so-
thought of this? Yeah.
Who thought of doing things like that? I mean, things are done all the time in terms of improving care for, like elderly or people in homes with dementia. Bringing animals in, do that give them comfort? Taking them to the shows, taking them to different places. Can you quantify the benefit of that in terms of their attitudes or their health or other measurements, right? It's fairly common, I think, to think about quantifying the benefit and providing a justification for paying for it. Right? So if you want to say, we need to, arrange this, we need people to do this, we need to rent the buses, right? It takes some justification to do it. Maybe you can do a few little pilots, but if you say you want to do it in a big way, right? So I have a brother who's a pediatric dentist, and we did a small study like this where, he did the data collection. So in New York City, a lot of the schools that are fairly large size, they might be bigger than St. Michael's in terms of population size, going to these elementary schools, is they have dental centers and health centers inside the school. Right? And so what's the benefit of having that inside the school in an area that typically is underserved or underutilized or disadvantaged in other ways? And so you can look at what % of the students at schools of that type versus schools that don't have those centers actually go to dental appointments every year? What percent show up on time? What percent get different types of care, right? And so, you know, or if you don't have it in the school, they have dental vans, right? So they have vans that can go to the school. So if you set it up so the van would go to the school, the children come out of their classroom, and with parents' permission, of course, then you treat them. You clean their teeth, recommend other care, refer them for the treatment. Doing it in the schools has an advantage that the parents don't have to bring the kids, get off work or something like that. There's less of an excuse, and it's provided there. If a school that's primarily getting government aid for free and reduced price lunches, they might qualify for free medical care as well under different programs, different health care, and so there's a lot of advantages maybe to doing that. But you would need to demonstrate it on a small scale before you argue that you need to spend millions and millions of dollars to do it overall. So this is, I think about this as kind of that type of thing. Hopefully it's done seriously. Right, so the data that get reported like this, and this might be just a snapshot of a bigger study. We might have done it over many different groups, maybe there's different activities involved and so on. The data that gets entered, if it's entered in just a Excel file, you know, there's a before column and an after column with the measurements matched together. That's going to be a different study. There, if you read these into R, you just can read it in. The museum data is just listed in there as an object before and after. Right? The last few observations are these individuals here. To do the t-test procedures in R, we're going to take the difference of those. Right? Now, this difference is all these 32 differences that are there. There's 32. I'm going to assign putting these little semicolons there allows me to put two commands on one line. That's not necessary. That's just, for the handout, it reduces space, so it saves paper. Right? The average of those is 7.625. I'm going to save it as something just d-bar, that little bar over that. The standard deviation of those is 5.272, so the standard error is this SD over square root of n. So the standard error actually is this 0.932. Degrees of freedom is 31. DF value in there is 31. The t statistic is the ratio of those things, right? So the t statistic is on the wrong place. In this case, it's actually about 8. Right? It's 8 standard errors away, right, from 0. There's a huge difference in terms of standard errors. We would compare that to, this is a quantile for a t, about 2.04 on Rosner's table, looking it up from that. Do we have 30? We have 30. We don't exactly have 31. But at 2.042, that would be pretty close to this number. In R, it gives us actually 2.039, just a little bit smaller than that. Yeah.
So back on the table, if like say we wanted the exact for 31, how would we how would you estimate it?
Yeah. So if you didn't have it exactly on the table, you can go down to the. I don't know how to get that. Get that. It just annoys me. Not sure how to change. But you can take the smaller value. That's conservative. Right, because it's going to give you a bigger value to compare to or to use in your interval. That's kind of conservative in the sense that it's making it a little bit wider than necessary. So 31 is pretty close to 30, so you could just use this one and say that's fine. If you say you had 35, kind of halfway between, you could kind of take the midpoint. Right, so 2.04, 2.02. If you use 2.03 and said that's the midpoint of these two, that seems reasonable. You know, the computer would give you some number in there. In a real project or for your project in your class, you can use the computer, get the exact value in there. But taking the smaller value is conservative, or something kind of reasonable in the middle. There's not much difference you know, between 120 and infinity is just a 1.98 to 1.96. So most things in that range, thinking 1.97, is going to be accurate enough for the class. It's not taking the 1.96 value because we're not actually normal. We need the t because we're estimating the standard error. And so a confidence interval, right? If we did this one, we'd take v bar minus a t times the standard error up to that. So our interval is 5.72 up to 9.52 for 95% confidence interval. So there definitely seems to be an increase, a significant increase in that, right? So you might question whether this is meaningful, right? So that number 5.72, right, so 95% confidence interval, or the average difference, which is the difference of the before or after minus before, d bar plus or minus our t value, s over the square root of n, d over the square root of n. So we got 7.625 plus or minus t value. What did we just say it was? For that, for 30, it was 2.04. So what if we say it's 2.0? Say 2.04 approximately. And then s 5.292 over the square root of 32. That gave us 5.72 up to 9.53. So on that health measurement scale, that's the average increase, right? So again, we can ask the same question: did handling the museum objects cause this improvement in their condition? It's a before or after study, so it'd be nice to have a control group, right? Some individuals who didn't get this, or got some other kind of standard stimulation, maybe where they don't leave, or they're shown a video on the museum or something, right, to see how much of a benefit is this actual trip to it, right? And it's even, you know, it's in a lot of things in psychology or behavior things, it's always a question of, is it actually this? Or if they had gone to an art gallery, would that have been the same effect as going to a museum or something else? There probably is some, well, this is a before or after with ill patients, so maybe they would have gotten a little better anyway. It would be really nice to have a control group, right, because they're getting medical treatment to see, is this gain bigger than they'd get otherwise? But there maybe could be many equivalent things that would have provided some, you know, stimulation and some benefit. And so it's be a bigger research question to look at all those possibilities and optimize it to make it really good for people. Now it's good to be able to do the command, you know, write out the formulas, plug in the numbers, do some of the computing in R. As you do your homework assignment, if you want to check some of the things, I encourage you to write out the different components to it. There is a t-test command in R. For the differences in there, right. The t-test, when there's only one variable listed in here, we'll do a test if is it 0 or not. Right. The alternate hypothesis, is it 0 or not? One sample t-test, it gives that t-value that's very extreme. The p-value is practically 0. This is scientific notation, so there's 8 zeros and then a 3, so less than 0.001. It gives a 95% confidence interval in there and reports the mean. If you don't take the differences initially in R, you could put the museum values after or the museum hour after before. If you just give it 2 columns, it thinks it's 2 separate samples. So you took one sample of people who went to the museum and another sample of people who didn't. You have to tell it it's paired. That's part of the design. You have to tell it that. And if it does that, if you tell it's paired equals true, it gives you the same results. This one called it a one sample t-test because you only had one column of differences. This one called it a paired t-test because you had after and before and you told it was paired. So, but it's doing the same computations. Yeah.
What's the significance of that statistic again?
The t-statistic, right, so this is going to be our test statistic, right? This is actually calculating the, in this case, the t-statistic in this case is our d bar divided by s of d over the square root of n. So in this case, it's about 8.18. And we would compare that to a t-value, 31 degrees of freedom, because that's a minus 1.975, 2.03 or so. And that's way beyond that. So we're going to reject the null hypothesis. That said that the difference is 0. One rationale for rejecting it is the t-statistic. Is so much bigger than our cutoff value. So our average is 8 standard deviations, standard errors away, which is just doesn't happen if it's really no benefit, no change. Now on, what is the advantage of pairing? Why do we like paired match studies? Where do we get an advantage to doing those? Why not do two separate samples? Yeah.
Kind of helps you form your basis of causation. You can't do it without control.
Yeah, so in a way, people end up being kind of their own control. That's particularly true in this third example we'll look at with twins. You do get a control in the sense that you have a base versus change. What about in terms of standard deviation? We haven't looked at the summaries yet. The correlation, the positive correlation, will ends up giving us, means that the differences, y minus x, has much smaller, can have much smaller standard deviation than x or y. So x and y can have huge variance, right? They can be very large values. But if x and y are highly correlated, then all the big values are going to be close to their neighboring, their paired up big value, and all the small values are going to be there. And the differences are going to be on a very much smaller scale. Right? So for instance, in this, and as a result, the standard deviation of the differences is going to be greatly reduced, right? So the standard deviation of the differences, in this case, is 5.27. The standard deviation of the museum, the after one, before, is 10. The standard deviation of the measurements afterward at the museum is 10, almost 10 as well. But the differences have this small standard deviation. You can look at the correlation of the museum variables. Before versus after, the correlation was 0.86. We haven't talked too much about correlation, and we'll talk more about it when we come to regression correlation. But it can't be more than 1. Right? So this is pretty high. Right? If you plotted the museum data, the before versus after, generally that's a pretty strong positive association. Like these are measures of health before and after. Pretty high correlation. So even though there's big variability in before, big variability in after, The differences are, looking at, before versus after, or kind of differences away from an equal line there. So it's, they're pretty small. The variability within this point cloud is much smaller than the others. So you get this reduction. In the other example from the traffic lights, what was that called up here? The red light data, what are the red light data? Are the intersections before and after, the standard deviation of the red light before is 2, the standard light that after. If you take the before minus, the difference is there. Well, it's a little bit smaller. It has some advantage to pairing there, but not as much. I think probably the correlation of the red light, those two variables, is 0.79, not quite as strong, right? If you look at the plot of those, there are fewer points. It's kind of a correlation. It's kind of dominated by 1. So it's a little bit noisier. But anyway, you get a reduction because they're paired. Right. One last example of this. So this one, making the big sure I'm getting the activities. Go ahead and read that one. Summary numbers, and then you could write out a confidence interval or set up a hypothesis test, or do as much as you can based on that. There's 107 pairs. R negative 1.9 plus 3 standard deviation. 1 p-value. Write out a confidence interval, or do a hypothesis test. As we're getting into this, you can keep working on it. There's something called a case control study. It's very popular in medicine. In this case, the cases are individuals with dementia, and the controls are the people without dementia, and they're looking at another variable. And they're looking in terms of leisure activity from 20 years ago. For these individuals to see if there's a difference in that rate, right? Now, it happens in this case, these are twins as well. questions? So what did we, so we do a computer comment there.
Okay, so for the lower limit, I got negative 3.873.
Okay. Right?
Yep. And for the upper limit, I got negative 0.033.
Just below 0. So what did you do to calculate, say, the lower one?
For the lower one, I did a t statistic. So I did like d bar plus or minus t times the variance of d over the square root of 10.
Plug in the various numbers, and you use this t, right, the 1.97?
Yep.
So if you look at the table for Rosner's, right, the 106, 107 pairs, 106, not exactly in there, but 95% is going to be between those two. So, you know, 100, no, it's between, did I say 1 point, what did I say?
1.97.
It should be, I should have probably said 1.99. Sorry about that. Oops. My bad. I didn't remember right. So I'd actually probably use 1.99 instead. Oops, I forgot. There was this 120 in the table. So I would probably make it just a little bit wider, but that's my fault. It would be 1.99. I think it's not going to change the answer all that much, but just a little bit. It should be kind of in the middle there. So sorry about that. Negative 1.953 plus or minus the 1.99. Correct that, and then 10.0821 over the square root of 107. Yeah, it's something very close to this. It still doesn't include 0. So is there a significant effect? Yeah, pretty much a significant difference, right? So this would suggest that among those that were, measuring amount of leisure activity, always not just one question, it's always a whole scale. Maybe it's an activity record book. Maybe it's a series of questions where you divide up the hours in your day or in the last week. Okay. And then seeing, 20 years later, it's a pretty good commitment to keep following these subjects. So we go from one study that was taking 13 people, or 32 people to see museum objects, to this, it's following a cohort of twins, identifying them, and seeing them 20 years later, find out what diseases they have, and then looking back. And I wouldn't think that just that leisure activity might, this one measurement might not be all the story there, right? There might be a lot more. It might just be an indicator of general lifestyle. So there might be a lot more to investigate, more things to put together, but it kind of builds on the evidence. It would support the idea that activity over a lifetime and exercise or being outdoors or maybe just not being so stressed out, being able to relax a little bit, eventually, has some important health consequences down the road. So that's the header study. So we'll come back on Wednesday and look at independent studies.
Yeah.
Thank you, Matt.
You want to just?
What?
Have a good break, Professor.
Yeah, it's good.
Little months fine.
Yes, wait.
It was fun.
Yeah. I got to a little bit of reading of the K-means, and I've been drawing up, introduction and
Okay.
stuff for the project. But I'll probably shoot you an email towards the end of the week, maybe get a meeting
Okay.
next week, because it's coming up in 3 or 4 weeks now.
Yeah.
So maybe just like a halfway point.
But yeah, so but if we meet, either later this week or early next,
Yeah.
just with basic questions and things.
That's perfect, yeah.
And if you think about it, there's a couple times that we're gonna meet, like, do basic questions.
That's
get things
perfect.
done, and then a few more details.
Because I figured as I work through the report, I'll have things that'll come up that I'll have questions about or I want to
Right.
learn more about.
Right.
So I figured if I can come in for a couple of minutes. I mean, Monday and Wednesdays are the good days for you, or?
Yeah, so anything works pretty much. I have these 2 classes in the afternoon.
Yeah.
So,
And then after these,
yeah, so
Okay.
before or after those.
Perfect.
And then Tuesday, Thursday, I have one class, 10:15 to 11:50.
yeah.
So,
Okay, perfect. Yeah. So that works. That works awesome. I'll shoot you an email maybe towards the end of the week if I
Okay.
figure something.
see you, Harrison.
How's it going?
You too.